Thank you. I'm here to replace the irreplaceable Tad Patzek, who is depicted on the lower left. Frank Mell was a co-author in the work that I'll emphasize, but I also, when I get to the total field estimates from various shale plays, will be using work led by Scott Tinker and Svetlana Ganometa of the Bureau of Economic Geology at the University of Texas at Austin. The work's been supported by the National Science Foundation, my collaboration with Tad Patzek by Shell, UT Unconventional Resources, and the field-wide estimates were supported by the Sloan Foundation. There are several publications to support the things that I will say. An article in the AAPG Bulletin came out last week. We had an article in the Proceedings in the National Academy about a year ago, and there are papers in the Oil and Gas Journal supporting the Sloan study. As you are all aware, because you're in this room, an enormous resource has been given to us, gas from shales, which is being exploited at a large rate. I'll be discussing ways to put together information that are available to us now to try to obtain and improve estimates about the magnitude of this resource going forward. One indication of the scale of the resource simply comes by subtracting the Henry Hub price from the Russian spot price of natural gas, multiplying and summing, and if you do that, you reach a sum which is now approaching about $1 trillion that our economy in cumulative and rough terms has benefited from the resource. Now, I'm putting up a number of unfamiliar faces. I'm a physicist. As I looked at, I intended as I entered this work to be building a coupled fluid solid model for hydrofracturing. Indeed, I've done so. But after having looked at the production data for about 2 years, it began to occur to me that there was a different thing that could be done with them. And I drew on the work that these people represent to me. Several of them developed the theory of critical phenomena, in particular scaling theories for critical phenomena. My postdoctoral mentor, Leo Kadanoff, is on the lower left, and I learned a great deal from him. I'm also showing Gregory Barenblatt, Ben Whittam, Michael Fisher, Phil Anderson, and Ken Wilson. Wilson and Anderson won Nobel Prizes for work connected with this. The basic finding, which I will employ the same basic idea in approaching the shale gas plays, is the following. It's possible to have systems that appear remarkably different at a microscopic scale. In fact, fundamentally and completely different. And if you look at them at that microscopic level, you would argue for ages over what is important and how you should explain them. But back out, measure properties in the proper reduced variables and plot them together, and you find that these systems are all fundamentally the same. The ideas turned into theories that were called scaling theories and universality classes. And this is I think this is one of the most powerful ideas that came out of physics in the 20th century. It's the idea that sometimes it's completely legitimate, even at a quantitative level, to look at a level of abstraction that no longer focuses too much on the details and find quantitatively accurate representations of a system that come from properly focusing your attention on the right variables. Now, what I'll be talking about are decline curves for the shale gas plays. And I'll get to well-by-well estimates. Well-by-well estimates, decline curves, traditionally had been done with production curves, for example, the ones due to ARPS. If you look at Shale Gas Well, on first glance, it's fairly clear that it cannot be described by traditional production curve, which sticks a pipe into an effectively infinite reservoir in the spatial domain. The whole point about stimulating a reservoir is that there's only a finite region, something approaching a box, although of course the shape will be more complicated than that, from which the gas can come, and when that box is exhausted, the rate will have to start dropping. So a minimally correct account of any shale gas well has to take that basic fact into account. Now, it is a tremendous oversimplification to treat a shale gas well as a stacked series of absolutely perfect geometrical planes from which gas leaves with perfect conductivity, and in between which there's a uniformly permeable medium for the gas to move in. That's absolutely ridiculous that you could use such a simple description. Let's do it. Now, this problem has been attacked, not very widely, but we're not the first people to view this as the fundamental starting point, and I have here expressions, for example, from an article of Dmitry Silin from 2012. There have been one or two other groups that use this as an analytic starting point, and I have some expressions from his paper. I'll quiz you on them at the end. That's long enough. Those were approximate, and I think that the number of parameters presented in them can do with some additional simplification. So let me go through that process with you. The setting, which geometrically is far too simple, is a finite volume. Gas flows linearly and escapes from the boundaries. The gas itself, and this turns out to be important, uses the real gas thermodynamics. So the true equation of state of the gas at the relevant temperature and pressure is employed. I'll go through some equations quickly to give you the briefest sense of the fact that some parts are treated realistically, whereas others are not. This is the one-dimensional equation, correctly treating all the thermodynamics. I've assembled up top a set of definitions: real gas superpressure, a diffusivity, scaled variables in which time is scaled, and the real gas superpressure are scaled. The final set being solved is really quite simple. The claim is that the entire shale play can be condensed into a set of really just a single effective diffusion equation with a set of simple boundary conditions placed in the box. This equation is really just a single equation for any given play. It can be solved numerically, but exactly, and here is the final result. There is a single curve for every play that describes the decline of every well in it. These curves are universal up to two numbers. Those two numbers have physical significance. One of them is how long the well will last. The other one is how much gas will come out. More particularly, there is an interference time which characterizes the time at which the box from which the gas is being drawn realizes that it's finite and that waves of departure from the two sides begin to intersect. The original gas in place is the other parameter. That's straightforward and is commonly defined. The recovery factor is obtained from the solution of the differential equation, but it really is just a single curve, and the final expression is that the cumulative production of gas is going to be given by the original gas in place times a universal function whose horizontal axis is scaled by this interference time. Just to illustrate the way that the solution works out, I show here solutions of the differential equation at its various points in time. I will use the scale time reaching around 0.6 as the criterion for interference to have become visible, and you can see that at this point the curve is just about beginning to reach the center of the cell and draw it down. So, a bunch of bold assertions about the nature of wells in these plays. Let's start doing comparisons. We first asked the field geologist to send us 5 wells that he viewed as good and typical, and he did, and we placed them on this universal curve, obtained the scaling parameters and put them there, and they fit rather well, which was encouraging. If you look at the production rate, it's much noisier for the experimental data. It does follow the curves, but it's not nearly as convincing as looking at the cumulative production. Okay, fine. So we hadn't selected them deliberately. Let's go to more wells. We took, this was in 2013, so we took every single well that had been drilled in the Barnett Shale that was horizontal, had not been recompleted. We're using the IHS-SARA database, so we were able to find wells that had been recompleted. We excluded those, looked at the horizontal wells, and put them all on there. They divided into 2 classes. First of all, there were all the wells that showed some evidence of interference, that is to say, a production beginning to decline due to coming from a finite box. Those 2,057 are on this curve, fitting, I think, quite well with the predicted single universal curve. The remaining 6,237 that were not showing evidence of interference should fit just a single straight line when plotted against the square root of time, and they do that adequately. Now, the parameters have meaning, and one can therefore extract them. So interference time and cumulative gas in place are actually extracted from the production history as parameters needed to fit the curves. And this is a plot for all of the wells where interference could be determined in the Barnett of the interference time and the original gas in place. You can see interference times ranging from about half a year to 5 years, and original gas in place ranging from about 2 billion cubic feet up to about 5 per well. We've also carried out this analysis now for a number of other plays. For the Fayetteville and the Haynesville, with some slight modifications, things went more or less as expected. The Marcellus is somewhat more difficult, largely because the data from the Marcellus are much more sparse. We're only getting it every 6 months, and this has made it much harder to get parameter estimates that fit within our error bounds. In addition, it's interesting, if you look at the Marcellus, you'll see that there are really 2 wispy bands of wells that don't fit quite perfectly on the curve. That's because they're actually at 2 different pressures. One set the reservoir pressure is around 4,000 psi. The other one, it's more like 8,000 psi. They're coming from different parts of the play. and so it looks as if a single curve may not fit them perfectly. Other than that, the basic structure of this comparison seems to be doing quite well. Something which we've noticed fairly recently, and I think that is interesting, is that there are actually strong correlations between the interference time and the original gas in place. Those three plays, the three plays for which we have the most data, I'm comparing here, the Barnett, the Fayetteville, and the Haynesville. There's a power law of about 0.75, and this regression captures about 50% of the variance. So I think there's more to be done. There are more physical parameters that can be used in order to try to predict the full set of parameters even when interference hasn't come in, but this is a good start. These are the decline curves that have entered the Sloan survey predictions of reserves and production from the Bureau of Economic Geology. This is the team led by Scott Tinker, articles, John Browning is the first author. These estimates include production from wells in the various plays up through the production from those wells that will have been drilled by 2030 and includes their cumulative production up through 2050. I'm not going to comment right now on their comparison with other estimates. They're in some cases lower, some cases higher than other published estimates from these from other sources. For the Haynesville and Fayetteville, somewhat lower. For the Barnett, higher than some other estimates. This is a Monte Carlo simulation that the group ran looking at the probabilities of various parameters that led to the estimates, including probability distributions of price. And I should say that this is the result of a large team working on the problem, and it includes a very, very detailed study of where it will be possible to drill wells and estimates about how price will drive the rate of well production. So the title referred to how much oil, condensate, and gas will be produced. I think that it's premature to present complete estimates of all of those things, but this is a pretty good summary of the form in which it's now possible to give accurate estimates from specific plays for gas. Work on oil has already been conducted, but it's still preliminary, and there's several other plays which are coming along and should be available quite shortly. There's one final thing I'd like to mention because I think it is interesting and may bring us back to one of the features of the original model that is fairly clearly unrealistic, namely the geometry in which these calculations are being done in a cuboid region. Let's suppose we go back, take laboratory values for the diffusivity, and then ask what must be the spacing between fracture planes to account for the observed production of the wells. I've plotted that for all the wells showing interference in the Barnett Shale here, and what you see is an effective spacing of around 3/4 to 2 meters. That's, of course, much less than the spacing between stages, but completely consonant with what field geologists say is the typical spacing between natural fractures. So what this tells us, I think, is that when wells are successfully producing, what they've done is to activate a natural fracture network that is considerably finer grained than the spacing of the stages with which the process begins. Apart from that, it's very difficult, based on physical law, I think, to account for the rate of production. Finally, I give a well-by-well account of how the expected total gas the well will yield compares with a volumetric estimate of the original gas in place. And what you can see well by well is, first of all, this was done as a sanity check because we shouldn't ever, from our model fitting, be getting amounts of gas that are larger than the original gas in place. And indeed, you can see that that works out very well. But then you look at all the others and you recover a result, which again is fairly common in the industry, that the well-by-well production is 10 to 20%. So the final picture that emerges from all of the modeling in the large is this, that the stimulation process creates a network which penetrates the impermeable shale and creates a fracture network with spacing on the order of 1 to 2 meters that's able then to recover gas at the rates that we see. However, it only encompasses about 10 to 20% of the available volume. So the technical challenge, if production is going to be increased, is to extend that fracture network with the 1 to 2 meter spacing to a greater proportion of the available volume, and production increases should follow. That's not part of any of the estimates, nor should it be, because right now the technology and the cost involved in doing that, I think, are very much unknown. As a physicist, I think it's fine for me to mention a possibility of that sort, but I think it would be quite premature to put it into anything like a field-wide estimate. So here's the summary. There's a universal form to well production. It doesn't match any of the traditional forms. It has a square root piece followed by an exponential piece, but I believe that the shape of this curve really is dictated by the physical setting. It's insensitive to details. It does depend on real gas thermodynamics, but almost no other detailed feature of the original setting appears to be crucial. There are two parameters that then scale this onto all the wells. They are an interference time and the original gas in place. All the wells fall into two groups, those that have demonstrated interference so far, and those which are still sufficiently young that they think they're infinite, they will live forever. They're sort of like adolescents, and they haven't yet started to bend over. Interference time and original gas in place can be estimated now for all of the interfering wells. We can probably do a decent job statistically of estimating them separately, even those that haven't shown interference, by using all the other physical properties of the well and a statistical model. These are the decline curves that have gone into the Sloan survey of shale gas production, which I think is the most detailed and accurate estimate for those plays where it has been taken of the reserves and how they will come out in response to various price signals. The spacing in the reservoir that one needs to have in the fracture network to account for production is 1 to 2 meters, and few wells recover more than 10 to 20% of the original gas in place. That's, I think, both a reality currently and a challenge to the future. Thank you. And since I spoke very fast, there's time for questions. Sure.
Yes.
Thanks so much. That was great. So quick question. Have you guys been able to explore how well this works for wells that are particularly wet? So wetter gas wells versus a poorly dry well, and whether you're seeing a lack of accuracy in terms of otherwise?
So there's a region in the Eagle Ford where you make a transition from gas to oil, and in the middle they are mixed. So we have a collection of data from those wells at our disposal and have been looking at them. I think we don't yet know exactly how well this model will work, whether it needs extensions or whether it is adequate. So far the indications are that even a simple interpolation between the two regimes where the equations are definite seems to be okay, but that's a premature accounting, and we'll be looking at this with greater care in the future.
Can you say anything about the oil plays in California, such as the Ventura, Los Angeles, and Maria?
I happily can say nothing about them because I haven't looked at them. I am quite sure that these methods could be applied, but I don't think we have those data right now.
Yes, we still have time for a few questions.
When you making a prediction of the future, you don't know the gas in place, so you're drawing from that statistical cloud. How does that work?
Well, in cases where interference has become visible, so the curve is beginning to bend over, if the theory is right, then we do get a prediction of the total gas. Now, there's an alternative source of information about the total gas, which is simply a volumetric estimate. You know the extent of the region, you know the horizontal, vertical, and lateral dimensions, you know the porosity. There are geologic parameters that let you estimate an upper bound on the original gas in place by that means. So that's an additional piece of information. Until interference becomes evident, our modeling doesn't tell us how much of that is going to come out, but I think we can actually do better by looking at correlations amongst all of the geological parameters. So with less confidence that we get from the model, but more than just a random guess, I think we'll get information on that.
Does the bend over include both the change in production of individual wells and the number of wells that might be drilled in a given area, so that you're getting fewer wells early in their history that are producing a lot?
So what I mainly emphasized was a physical model for the production of a single well. But in order to obtain field-wide estimates of total production over time, the Sloan team has indeed put in mathematical models for the drilling of wells that depend both upon the available area, the possibility of interference, avoiding cities, and the economic drivers that come from gas prices. And they've actually produced a series of estimates that suppose different price histories and then ask how would those send signals that would then affect production down the line.